All right, let's get going. Thank you for coming to the center for fall 2024. It's our first talk of the year here at the center. Welcome to all faces, or older, or people who have been here before, and the new faces, people who are new at the center, the new fellows, the postdoc. So really a great pleasure to see you. We have a full schedule this semester. All the talks are online on the calendar, so have a look for the lunchtime talk, the ALS lecture, and so on and so forth. I'm really glad to see so many people. That's the advantage of taking David Wallace forefront, that we draw a large crowd. It's a real pleasure to see you here. Before introducing our speaker, let me tell you a bit about a few events in the coming in the coming days. On Friday, Kevin Zollman is going to be giving a lecture from going to come from CMU, and the talk will be authorship norms and epistemic public good. So come to listen to Kevin's lecture. On Tuesday next week, the talk is given by a former fellow. It's part of the series featured former fellow. So the talk will be online. If you want to have access to the talk, you need to go to the website, and you'll find a link for the Zoom lecture. And the talk will be given by Soazic Lebihan, who will be talking about how to secure public trust in value-laden science, a fiduciary model. So if you're interested in trust in science and value and science, please join us on Tuesday at noon on Zoom for the lecture by Soazic Lebihan. And the first annual lecture series will be given by Thomas Reichmann on the 27th of September at 3:30 on the 10th floor. And Reichmann will be talking about Niels Bohr, transcendental physicist. So you're also all invited to this lecture in 2 weeks from now on the 10th floor. Now it's my pleasure to introduce my colleague, David Wallace, who holds who is a Mellon Professor of Philosophy of Science. He has a joint appointment in the Department of History and Philosophy of Science across the hall, and in the Department of Philosophy on the 10th floor. You all know David, so I won't spend too much time going through his work. The philosopher of physics. He's worked a lot on the quantum foundations of physics. He has recently published 2 books. One of them is a shorter book, which I already mentioned that last time I introduced David, but for someone like me who is not an expert, it was actually a real pleasure to read. It's Philosophy of Physics, a very short introduction. So for non-philosophers of physics, I highly recommend that book. Very well written, very clear. One really good introduction, I think. And one which is a bit more for the specialists, but a classic now already, is the Philosophy of Physics in 2012 with OUP, The Emergent Multiverse, Quantum Theory According to the Everett Interpretation. So very influential and very well written in the philosophy of physics. David, of course, has published widely in all the journals. That's only one page of his CV, so I won't go through all the articles. There's many other pages after that. So just take a good journal in philosophy of science, an excellent journal you know David has published in there. That's a good heuristic. He's also something we should all be grateful, very minded with respect to helping the community. And he's indeed the editor of Philosophy of Physics, the new journal, an open access journal. You're still editor, right? Yes. You're still editor. Yeah, and which, you know, it's a lot of work to help create a new journal. It's a lot of work to edit a new journal, and it's open access, which all should be supported. So I'm actually extremely grateful that David is doing that in addition to all his work. And so thanks for being our first speaker. Today, David will be talking about learning to represent. So it's yours.
Thank you for that. Very generous introduction. I'll start with a very quick disclaimer. As Edward says, I'm a philosopher of physics. I have heard there are other sciences. The mid-20th century approach of philosophy of science to those other sciences was either to deny that they existed or to assume that they could be subsumed under physics. I gather this has turned out to be premature. I am specifically going to be talking about theories in physics, and I leave to future work, probably by other people, to explore the extent to which the things I'm saying do or don't have implications in the sciences beyond physics. So I very much welcome questions and exploration in the discussion from people experts in other sciences, but my kind of caveat is I know my territory and I know to stay in my lane, and I specifically will have physics in mind here. I'll often not say that explicitly, but in this sort of audience, I think it's worth stating that. Okay, so here's the starting point of what I want to talk about. There's a distinction in the philosophy of science literature that traditionally has been cashed out as a syntactic versus semantic conception of theories. I, for various reasons, prefer the phrasing language first notion of theory compared to a math first. What I mean by something is this: on the language first or syntactic conception of theory, which I think it's fair to say was the sort of dominant assumption about what scientific theories were in the sort of heyday of the logical empiricists in the middle of the 20th century. On this kind of notion of theories, a theory is a collection of sentences in some interpretive language. There's a notion of a formal theory you could discuss, but the point of view of what a scientific theory is, it's a theory in natural language or some interpretive semi-formal language or whatever. The relation between theory and world is linguistic, understood in the tools of language. We use the sort of tools of the notions of sort of reference and satisfaction and truth and so forth that we're familiar with from the broader questions of philosophy of language. It's become fairly widely recognized in modern philosophy of science that, again, at least as far as physics is concerned, that notion of theory-world relation and that notion of what a scientific theory is highly deficient and most partial. If you want the version of this kind of story that applies in classical mechanics, you need to talk to Mark Wilson. I'll talk more in the areas of sort of 20th century post-quantum physics. What you will systematically find is that the way theories are presented, although there were of course no words in the textbooks and monographs, but the words generally serve to frame and heuristically explicate things that are presented in a mathematical form. And you can kind of see how this plays out if you ask difficult questions to anyone in theoretical physics. You want to ask someone, for instance, why does the charge of the electron get stronger at short distances? You might initially get some verbal explanation. Well, it's about the renormalization process. And if you push, you might get something a bit more. You might get, well, the vacuum is polarized and positive and negative charges are pulled out of the vacuum. And then, again, it continues the sort of linguistic description. And if you're sort of trying to understand this in a popular science context, that's going to be fine. But if you're the metaphysician pushing at this and you want to know, well, exactly where are they pulled out of the vacuum? What do we mean by these things? Eventually, the physicist you're going to talk about is going to drop those heuristic descriptions, going to go to the blackboard, it's going to write an equation and say, this is what I mean. And the explanation is still going to go back and forth to various kind of linguistic hooks, but a core part of the work is going to be done. On the sort of purified version of that, and the reality is inevitably a bit messier, but it's convenient presentationally to think in terms of purified version. On the purified version of that, a theory in physics shouldn't really be thought about as a linguistic entity at all, more something like a possibly structured collection of mathematical models. And the theory-world relation is going to be mathematical representation. And there's a lot to say, a lot I have said, a lot others have said about the relation between these different views, about why one might be motivated to adopt one or other view, what the metaphysical consequences might be. But my focus in this talk is going to be the last two words in that description, mathematical representation. Because if the sort of theory-world relation is to be cashed out on a language-first conception of theories in terms of something like linguistic notions of truth and satisfaction and so forth, we clearly need some understanding in parallel of what the supposed mathematical representation relation is, but puts a mathematical structure in a representational relation with some part of the physical world. And much has been written on that topic, but a vast fraction of it falls under this very general schema. is Mark's favourite theory T, but I hope it's turning up in a sufficiently abstract framework not to cause trouble. Mathematical model, or in any case, this is in a certain sense the opposition position. Mathematical model or class of models T represents a physical system P if the following hold. So firstly, T's got some list of features ABC. And secondly, P has got some list of features X, Y, Z. And there's some kind of relation that holds between the ABCs and the XYZs. There's some features the physical world has, some features the mathematical world has, some correspondence that holds between the physical world features and the mathematical system features, and it's in virtue of that that T represents P. Let me give a couple of examples actually before moving on from that. So a highly influential model of representation is the sort of picture that representation is something like an isomorphism. So it's something like, well, the mathematical thing is structured such and such a way. The physical world has such and such structures. Maybe it has such and such objects standing in such and such relations with one another. And there's an isomorphism in the mathematician sense between that mathematical structure and the physical structure. So you can see it in other places. I mean, here's a very different account of representation. If you look at the sort of general Gricean account of representation that Cohen and Callender had advocated, on that kind of picture, it's something like T represents P if the scientist doing the work intends T to represent P. So Callender and Cohen say, I can perfectly well decide to use a jellyfish to represent a quantum system. If I want to. It's not usually a good idea, jellyfish sting, but it's up to me how I represent. It's a free country. I declare that my jellyfish represents this physical system. But of course, even on an account like that, if you want to do any concrete scientific work in some representational story, you need to articulate the details of that representation. I can perfectly well say, by fiat, this system of mathematical equations represents the movement of this space probe, but I can't use that to construct the space probe, work out how to program it, work out how to fuel it, unless I can say a bit more of the detail. I can say, well, the coordinates in this mathematical representation represent the points of space. The trajectories here represent the paths taken by the rocket. The differential equation represents the dynamical law governing the rocket's motion. And so again, notice what you have to have. We have to set that out, I have to be articulating the physical features of the world and the mathematical features of the world and talking about a relation that holds between. So I want to suggest that this kind of schema, never say that something's universal in philosophy, but is extremely widespread in the way people think about representation. And it contains a threat of circularity, and this has been recognized. So the only way we get that scheme going is if we're already able to describe P as having features X, Y, Z. How do we do that? Well, we could have done that in some more mathematics. We could have said, look, I can represent the system as having features X, Y, Z. And then, given that I've represented as having features X, Y, Z, and given that features X, Y, Z are in correspondence with features A, B, C, then I can represent it with this piece of mathematics. But I can only get that going if I already have a mathematical representation of the system. And so the worry there is that this is a kind of idea courts an unavoidable circularity in any attempt to understand mathematical representation. Representation presupposes representation. And if one were to avoid that circularity, one would have to have some way of characterizing the X, Y, Z that characterize the system other than through mathematical representation. The obvious possibility being description in language. So insofar as that's right, even what I've been calling a sort of math-first approach to theories, a math-first approach to philosophy of science, and physics, if you like, is in some sense tacitly language-first. It presupposes ultimately that prior to doing and understanding the mathematical representation, there exists, perhaps even I'm in possession of, some account of the theory in language that can be placed in correspondence with the physical theory, with the mathematical representation. And you might imagine some kind of bootstrapping story, and then you see some of this in the metaphysics of science literature. You might think, well, what's going on is I start with my descriptions in language of the manifest image. I have some mathematical theory, part of which I put into correspondence with my description of the manifest image, part of which is initially instrumentalist, but I can conjecture further facts about the world, further unobservable objects with unobservable properties standing in unobservable relations, which can then in turn be put into correspondence with more of the mathematics, and on that basis I can posit that the unobservable bits of the mathematics are already also doing some representation. And maybe there's something underdetermined about that, but perhaps we have to just be relaxed about the underdetermination of the world. In any case, we seem to need, on pain of this circularity, some access to this kind of, certainly non-mathematical, doesn't seem many options other than that, other than something verbal, linguistic to describe it. So, slightly missing fact. So just to sum up, here's the setup. If that were true, well, okay, I should say the ulterior reason for a lot of this talk is presupposing that something like this is true is overwhelmingly the most substantial pushback I've had from my attempts to develop various forms of structural realism, of math-first approaches to physics. I've had that kind of response ranging from everyone to people in sort of high church analytic metaphysics to fellow travelers in structural realism. So my sort of secret reason why I care about this is, well, not very secret, I told you, but never mind. Secret reason I care about this is because of how it impacts on the sort of broader scheme of how to think about scientific theories in a way that gets that puts metaphysics and epistemology in kind of closer contact with scientific practice. But here are some more sort of in its own terms problems I want to raise. So the first one is you have what you might call opacity of representation. In something like my space rocket case, you can kind of, you do in fact probably have some antecedent understanding that maybe you can verbalize about what I mean by spacecraft and rockets and places in the solar system and so on. But I'm going to go out on a limb and guess that you don't have a comparably solid linguistic description of quarks and gluons, or others of the esoterica of modern physics. You don't need to go that deep even. The spin of the electron is already a fairly demanding case. We have rough and ready heuristics for these things, but those heuristics are nothing like the sort of full description that could be presupposed in mathematical representation. To pick an example I may have used in this audience before, sometimes we say that the proton is composed of 3 quarks. The idea that that's true in some literal verbal sense in the sort of philosopher's notion of mereology and composition, and the proton is composed of 3 quarks in the same way that the table is composed of its top and its legs, is somewhere between huge pedagogically helpful simplification and a story retention. So the reality is that what we're given of the sort of deep world of quantum physics and particle physics and early universe cosmology and the interior of the sun and so forth is given to us mathematically presented. And we just don't have access to those sort of verbal descriptions. Physics is just not in the business of giving them to us. So we don't seem to have that other thing to which theories could present to us. I should pause and say that some people would say, yes, that's exactly what's wrong with 20th century physics. Physics went wrong when it started presenting itself in this mathematical way and not giving actual clear statements of what there is and what it does, what the ontology is and what the properties are of the ontology. And there are others who say, no, it's even worse than that. Because all the rot started with Galileo. However, I have more naturalistic inclinations, so I'm going to take as read that the fact that we have this kind of opacity is a real problem for any account of scientific representation. There's another problem here. If what it is to actually explain representation is to give the correspondence between the verbally presented description of the system and the mathematized theory, then since physicists aren't in the business of doing that, it's going to follow that physicists actually don't know how their theories represent. The physicists lack an account of how their theories represent. The crude way of putting that is, do physicists even understand their own theories? But now the Maudlin and certain people will say, well, no, that's the problem with physics. But even philosophers friendlier to physics have actually often embraced this as a kind of division of labor. There's a conception of philosophy of physics where doing physics and doing all the calculations and working out the approximation schemes, that's what physicists do. And interpreting things, that's our job, that's what philosophers do. I have some problems with that way of thinking, not least that it's kind of heuristic. But also, I want to suggest, I mean, who here knows general relativity? Do you understand? I know general relativity. I think I understand it reasonably well. I haven't got my verbal description to put it into correspondence with. So there's some problem with the idea that this notion of representation is not. If I have to have a language-first notion of representation, it's just not going to have the resources to explain the fact that practitioners of scientific theories do, in some sense, understand those things. But what's the alternative? Aren't we forced into this by the circularity of any account of representation, of mathematical representation, that presupposes mathematical representation? Isn't there kind of no alternative to this way of seeing? But the main point of the talk is to sort of sketch out an alternative. Here's the basic plan of the talk. I want to say, yes, there is a circularity in an account of mathematical representation that presupposes an account of mathematical representation, but it's not a vicious circularity. In fact, it's a circularity we're already used to from our extant theories of how language describes the world. And in that context, we've learned how to live with it. And I'm going to start by reviewing a little bit of the sort of philosophy of language and show just what I mean by that kind of non-vicious circularity. And I'm going to argue that once we understand that, we can construct non-viciously circular, but still circular, accounts of mathematical representation along very similar lines. And finally, I'm going to say that once that's recognized, it ceases to be the case that we have good reasons to think linguistic descriptions are prior to mathematical. This is perhaps a good point to just restate my comment right at the beginning that the extent to which these things apply beyond physics, I think, is open to question. I think it's pretty clear that physics theories are much more mathematized than theories in most of the rest of science, and something like a maths first idea about how representation works in other sciences is going to have to be much more problematized and complicated and probably a lot more pluralistic. And again, I leave that for future work and for future discussion. So let me get going on that project. Let me give a kind of view from 40,000 feet picture of very crude takes of how we might think about meaning in language. So take a word, take Pittsburgh, not Pittsburgh, take Pittsburgh. Now, how do I explain what Pittsburgh means? Well, I'm sitting in Pittsburgh, so I could in principle point to it. Even that's kind of tricky. I can say this is Pittsburgh. Well, did I mean the Center for Philosophy of Science, the Cathedral of Learning, Pittsburgh, Pennsylvania, the Milky Way galaxy, this square meter of floor? In any case, we didn't necessarily have to be in Pittsburgh. If you'd asked me what London was, I couldn't use that particular tactic. It's too far away to see, no convenient news. So normally we recognize that in most cases, the kind of ostension just pointing is extremely limited, extremely ambiguous. Mostly what we do is definition. I can say to you, Pittsburgh is the city, well, here's a sort of ostension description mixture. I can say Pittsburgh is the city I'm currently in. But if I don't have that tool available, I can say Pittsburgh is the largest city in Western Pennsylvania. Pittsburgh is the city where the Cathedral of Learning is. Pittsburgh is the city at the confluence of the Allegheny and Monongahela rivers. Pittsburgh is the city that Kamau Harris was in yesterday morning. There's definitely many descriptions of this kind, but of course those don't define the word. And even for words, even when I'm not dealing with a proper noun, even when I'm dealing with some descriptive words, the definitions are to some extent imperfect. And more importantly, from the point of view of what it is to talk about meaning in a language, I'll come back to that in a second, then the definitions are using more words. And so if you want to know what those words mean, I can either explain that through ostension, or I can explain it through more inter-word definitions. There again is a sort of circularity of the presence. If the meaning of a word is constituted by its description in more words, and the meanings of those words is constituted by the description in more words, how does all that bottom out? Now, the logical positivists had a theory about that, of course. They said it bottoms out precisely in ostension. There are some words whose meaning can be understood very directly by their relation to things we can ostent. sense data, medium-sized dry goods, some kind of things of that kind. And everything else can be understood by its relation to those notions. Something like the verification principle for the positivists is the idea that precisely because meaning must terminate in a chain of definitions, so it must be given by a chain of definitions that terminates on the given, then of course any two such chains of definitions that terminate on the very self-same pieces of the given must have the same meaning, and therefore the claims, any attempt to say one of those is true and the other is false is meaningless. It's false, but it's meaningless to make that distinction. We all know the logical positivist project failed. I'm not going to rehearse the reasons why it failed. I rehearsed this partly because I think a lesson one often gets from sort of undergraduate philosophy education in the 21st century is that the reason it failed was because the logical positivists were idiots. This is not true. They had a genuinely serious problem and they advanced the principal solution to it, which doesn't work when you try to fit the details. What else could we do? Well, we could try constructing formal theories of meaning. Again, we end up using more words to do that. Here's the classic example from Tarski. Snow is white is true in English if snow is white. That's an accurate statement. It's not going to teach you what snow is white means unless you already know what snow is white. Sorry, what snow is white means. In contrast, Schnee ist weiß is true in German if snow is white. That is genuinely informative. It does genuinely teach you what that German word means, but only because you antecedently possessed an English phrase that did the same descriptive work and you just established a synonym. So is there a circularity again? Well, there have been ways to try to move beyond it. I've given you the positivist example. They could either genuinely uncertain account, but ultimately it's just not fit for practice. The post-positivist position is something like, we do understand our language to start with. It doesn't make sense to start on this sort of fiction that we don't understand our language. We understand it. We can build out from that, but we don't need a non-linguistic starting point prior to our understanding of language, and we can't get it. We couldn't get it even if we did it. It's obligatory here, I think, to put the quote from Nurek that find it so much to popularize. We're like sailors who on the open sea must reconstruct their ship, but are never able to start afresh from it. Where a beam is taken away, a new one must at once be put there, and for this the rest of the ship is used to support. In this way, by using the old beams and driftwood, the ship can be shaped entirely anew, but only by gradual reconstruction. In other words, the starting point is a substantial amount of linguistic description embedded. We can add new bits of it, we can even get rid of old bits of it, but everything presupposes a big bit of it to start with. No starting point. I mean, if I had to actually give a candidate for, what's the one bit of wisdom I think we have actually got out of the last 500 years of philosophy, then I think there being no sort of privileged starting point from which you can build everything else up, no Cartesian cogito starting point, no logical positive starting point, might be my candidate. It's extremely well motivated to look for such a starting point. Some extremely smart people work extremely hard to construct it. It doesn't work. You can kind of see for many reasons, ranging from sort of pure logical reasoning about it to what we know about human biology, to be pretty confident why it doesn't. So back off then and go to a bit of detail. Let's present this as a concrete problem to see the sort of circularity in play and see why it's arguably not vicious. I'll put this in terms of theories as much as language, but here I very much mean the language first notion of theory. I'm trying to make contact here more with the philosophy of science literature about theories than I am with scientific theories. Right? So here's the problem. We already have an old theory O, an old bit of language describing some system. And we're presented with a new theory N, and we're given some understanding of the overlapping vocabulary that O and N have in common, the direct translations between O and N perhaps, and also some idea of how, following the sort of Hegelian idea of reduction, how we might derive claims in the old theory from the new theory via some kind of bridge principles. It is mean kinetic energy. That's the sort of example. Okay, so then how do we come to learn N? We understand O, and X hypothesis we understand O. How do we come to understand O? Well, the positivist's answer was you don't. O, X hypothesis had all of the manifest image language in, all of the given language in. N doesn't have any additional meaning except via its function as a calculational adjunct to O. Don't ask what the meaning in the normal sense of electron is or something, just understand electron talk as something which has consequences derivable in the antecedently understood language. We don't think that works. Here's an answer that we tend to think is close to work. David Lewis's answer in his How to Define Fundamental Terms. We will construct a new theory of meaning for it. But that theory of meaning is inherently tied to O, and our understanding of N rests on understanding of O. So to pick up one of the philosophy of mind examples was very motivating here, we'll say something like, if I want to know what pain is, again, example is oversimplified to the point of wild implausibility, but blame Lewis, not me. We want to know what pain is, then we have something like an antecedently understood theory of human behavioral psychology. There is a theory term for pain in that that's kind of a placeholder, and we identify that placeholder down as the unique thing in our lower level neuroscientific theory, which plays that role. So this is a case where, and again, I'm going through this quite quickly, and we'll ask those of you who aren't familiar with Lewis at all to take this on trust. But what we have there is a genuine theory of meaning where the talk in the new theory is not just a sort of calculational black box, but it's permanently glued to the old theory to get its sense of meaning. Our understanding of the meaning of some theory term, whether it's pain or proton, is permanently cashed out through its connection to terms in our language. There's a third answer that you see in modern metaphysics. I'm calling it here Sider's answer, though I think it has a lot to do with Quine's answer. And Lewis himself, in fact, was always talking about how we originally learn what a theory means. And I think Sider's answer is not necessarily compatible with Lewis's. Sider's answer is, well, Lewis is right at first. That is initially how we learn what N means. And initially our understanding of N is parasitic on our understanding of O. But after a while, we get the hang of it. We've used N sufficiently to understand N in its own terms. And at that point, our understanding isn't derivative on O anymore. And there's a kind of shell shift. We're no longer understanding the new theory through its partial translation to the old theory. We're understanding the old theory through its partial translation. I mean, a quick example of the kind of thing I think people have in mind here, if you think about terms like force and energy and work, those are, I mean, first of those who know the history of this much better, but at a very loose level, those at least have some level of normal meaning, and they're not introduced by 17th century physicists as totally arcane new terms. They're introduced for a reason. They're supposed to partially get at the notions that are assumed to be antecedently understood in people's pre-Newtonian folk physics. But right now, of course, if you learn about force and work in school, then you're learning the Newtonian notion. And the Newtonian notion is authorized to correct mistakes made about what the word force means in folk usage. I want to just pause and give an example and say, just to illustrate these ideas in just a more fragmentary area of language, quite a long way away from science. So take the word lachrymose. Who knows that word? Somebody want to tell me what it means?
Tearful.
Tearful, yeah, not bad. Any advance on that? I mean, you're in good company. Given to tears or weeping is the Merriam-Webster definition. But what do you think about the following sentences? My 6-year-old has colic. He's lachrymose. I work in the local restaurant. Mostly I have to chop onions. I'm lachrymose. Now, those clearly aren't, if you know the word lachrymose, you recognize those are either wrong or they're weird affections to make a rhetorical point. So that's the Merriam-Webster definition. It's probably about as good as you could do in a succinct definition because dictionary writers are good at their jobs. But you can see it's not getting at the full meaning of lachrymose. And in fact, the dictionary writers help you with that. They give you kind of examples of usage. So Merriam-Webster has tended to become lachrymose when he was drunk as an illustration, to kind of get you to grok the idea that lachrymose makes sense in that context and doesn't make sense in the context of the colicky infant. You could give a formal meaning, of course. If you didn't know what lachrymose means, here you go, you're welcome. But the real point, of course, is to learn what lachrymose means, is to get the hang of using it correctly. There isn't really a way of saying in words exactly what it means that subscript is. Almost no word is exactly definable in other words. You get the rough idea of what it means by its translation into your already understood theory. But after a while, you've got to hang it. And after a while, you know how to use it. And the judges of whether you know to use it are either other people in the community who know the word lacrimose, or theoretically, they're linguists who have a detailed theoretical, human or alien linguists who have a detailed theoretical understanding of lacrimose, have an actual theory of meaning for lacrimose, which in turn is abstracted from human behavior, and check whether you use it correctly. So with that example in mind, with that kind of idea of how we learn new theories in mind, let's try to ask non-circularly what it is to understand them, which again, according to these sort of philosophical traditions. So 2 answers really, both generalizing the lacrimose example. There's an internal answer. You understand a language if you're judged to understand it by other people who understand it. External answer, to use the language according to its theory of meaning, as worked out through radical interpretation, through treating humans as just moving blobs to which you theorize, by external observers. Now, in either case, we already need a language to do that. The external observers who are judging whether I understand English need to understand English. The external observers who are formulating a theory of meaning for English through sentences like Schnee ist weiß is true in German, even only if snow is white, they already need a language adequate to describe all the things humans are doing. If their language doesn't contain sufficient resources to talk about crying humans, they won't be able to state that theory of meaning for lacrimose. They don't necessarily need to have a synonym for lacrimose. We're familiar with the fact that many words in languages don't have exact synonyms in other languages. Words like schadenfreude we just borrow directly. And for all I know, lacrimose has no exact translation for some languages. But either way, we need a language rich enough to describe the phenomenon. That's philosophy of language. Let me now turn some of those ideas to how we learn theories in physics. And the suggestion is that we can construct non-viciously circular accounts of mathematical representation along very similar lines to what I did. So I want to think now about how one goes about learning general relativity. About half the room or a third of the room put their hands up and asked, do you know, learn general relativity? So this is now aimed at the other 2/3. Step 0. If you've got a student who wants to learn general relativity, this is not as safe in a philosophy context as others, but in a normal physics context, the student who wants to learn general relativity already knows lots of physics. If you haven't studied F equals ma, it's not usually a good idea to jump straight into general relativity. In fact, generally speaking, in the structure of a physics education in Britain and America and broadly, the students start already knowing a bunch of physics. They know classical mechanics, they know electromagnetism, they know special relativity, they know the Newtonian theory of gravity. And when I say know, constitutive of their knowing is that they are able to represent a whole lot of systems using that physics. They know how to represent light, electromagnetic radiation, as a traveling disturbance in the electromagnetic field. They know how to represent the Earth-Moon system. They know how to represent a body moving freely under gravity. They know how Minkowski space-time works and how to represent a traveling twin who goes away and comes back younger than their stationary twin on Minkowski space-time. If they don't know that stuff, they don't know classical mechanics, electromagnetism, special relativity, and gravity. And of course, if you're learning general relativity, you don't know this stuff, go back to step -1. But at the point at which one is able to learn general relativity, one knows that kind of stuff. So then you learn the formal features of general relativity, the mathematical structure of things. And then you learn some translation schemes that let you map between general relativity regimes and regimes you already understand. So you learn typically quite early in education general relativity, you learn about the precession of the perihelion at Mercury, the fact that the orbit of Mercury is not quite the same in general relativity as it is in Newtonian physics. So you're helping yourself to the way in which Newtonian physics represents the orbit of Mercury. You're then using your translation scheme to map general relativity's account of the orbit of Mercury onto that description, and then you can see how general relativity gives a different prediction and suggests that, and how general relativity is claiming that Newtonian physics is misrepresenting. Similarly, if you look at early in a GR education, you'll learn gravity waves, and you'll understand gravity waves as a wave. You already know about waves. You've studied waves in water. You've studied waves in electromagnetism, and there's a whole bunch of verbal glosses and heuristics. You'll learn about the idea that the metric describes curved space-time. You'll be given the analog between curved space-time and curved space, which incidentally misleads a ton of students because curved space is not, of course, objects that go into circles, but that's another story. You'll learn these ideas and you get the hang of it, and you'll use this to be able to solve GR problems and discuss GR with other students learning it and check your understanding with your teachers. But there comes a point where you have to step beyond these things. There are gravitating systems which can be misrepresented using the resources of Newtonian physics, but there are others that can't be represented at all. Gravity waves look quite a lot like electromagnetic waves in the weak field regime, but not all fields are weak. Eventually, you reach a point where the student understands the limitations of the translation scheme heuristics. They're proficient enough that now they can see how those schemes can be understood in general relativistic terms, and they reconstruct their understanding of the modeling capacities of their old theories in terms of the richer environment they get for general relativity. And that's what it is to learn general relativity. That's how rather one learns general relativity. But then step back and ask the question we came into. What are we saying about the student when we say that student now understands general relativity? Well, I think, again, there's an internal and external answer to this question. The internal answer is the student understands general relativity if they are judged to understand it by other people who understand general relativity. And there's an external answer, which is if you suppose the space aliens who are observing humans and who, for a process of radical interpretation, have worked out how humans, what humans' theory of general relativity is, and have understood in the process of radical interpretation the correspondence maps between the humans' general theory of relativity and the aliens' own mathematical theory of space-time and the motion of planets and gravitational waves and so on. If the aliens establish that kind of translation of human usage, they can then use that to check if the student is using general relativity correctly or not. But either way, notice, we presuppose an ability to represent. In the internal case, we presuppose that the other scientists know general relativity. But even in the external case, where we don't want to treat that as a primitive, the external interpreters of humans who want to say, yes, the human student, or indeed the human expert, is using general relativity to represent, is doing it because they're establishing a correspondence, not between the human mathematics and the world, but between human mathematics and the mathematics the aliens already know how to use to represent. So I'll give a name for this kind of account of representation and spell out the details. For reasons I'll come back to in a second, I want to call this the TT account of representation, which stands for theories and theorizing. And it has these two components. Firstly, there are two things in the table. There are interpretive theories, which are formal objects, and then there's theorizing, a human community practice. So interpretive theories go something like this. Given some class of systems, and given some mathematical structure S that represents those systems, a theory for that class of systems is a mathematical structure M plus a structure-preserving map of appropriate kind, isomorphism roughly, or embedding or something, rho from M into S. In other words, what a theory is on this basis is a piece of interpreted mathematical structure, where an interpretation of mathematical structure is a map into a mathematical structure which represents the system. So observe the circularity. I presuppose that S represents the system, and then I explain what it is for M to represent the system via its correspondence with S. Those are what theories are, formally speaking. Then there's theorizing. Community is using M to represent via this map, just in case that's the best fit assignment to theory to their scientific activity. So you've got this whole bunch of humans drawing things on whiteboards, building interferometers, publishing papers, making films about what happens when you go close to black holes. What makes it true that that theory is using a theory which can be described as the formal mathematics of GR plus a map from that mathematics into something that represents those phenomena, is that making that assignment is the best fit to make sense of human behavior. And again, jumping back to the relevant philosophy of language, I call that a theories and theorizing approach, because I think it's an extremely direct parallel of the languages and language approach to thinking about linguistic meaning in the light of the things we were saying earlier that David Lewis proposed some while ago. So for Lewis, there are languages, formal things, which have theories of meaning that correspond to the objects and properties and relations in the world, which have to be described in some language to state the theory of meaning for a language. And then the human activity of language, whereby it's true that some human community is speaking a certain language if that's the best fit. There's room to worry about the details of how those accounts play out, but the main point I want to make is that you can take a very mainstream take on how to think about meaning in language and have a very direct parallel in the case of mathematized representation. So, claim. We can construct non-viciously circular accounts of mathematical representation along basically the same lines we did for linguistic representation. And now the third point of the plan, once this is recognized, there are no good reasons left to think that linguistic description is prior to mathematical representation. And I'll suggest, I want to sort of push that case stronger. And I want to sort of, if you like, contrast the sort of mathematics first representation account I've given, what you might call language first representationalism, which is kind of what we alluded to at the beginning. According to the language first representationalist, in the first instance, we describe the world in language. And then, sure, there's a subtle question that philosophers of language can worry their pretty heads about how it is that languages are learned and how they can be, how we can get apply them in new situations. Linguists, philosophers of language, metaphysicians can worry about that, but we're going to assume it's solved. And with a solution in hand, we're going to move on to the separate question of how mathematical models represent. And specifically, once we've solved it, we now have the resources to directly describe a physical system in language. And so we've got a relatively clear idea that we can give an account of mathematical representation via its relation to that description of language. That's the rival position. So why might we think that? Well, one reason, the most obvious reason, is just it's the only game in town. It's the only way to give a non-circular account of scientific representation. Well, I've tried to argue that's not the case. I've suggested that the circularity you find in mathematical representation is not a vicious circularity, but anyway, it's the same circularity we find in philosophy of language in any case. There's no alternative to an account of linguistic representation that presupposes access to linguistic representation. What else? It's beyond our cognitive capacity to understand the world except for a linguistic description. I'm sorry. I don't think that's the case. I think we, the scientific community, seem to manage fine with our theories of physics, even though we don't always have these kind of linguistic descriptions. But also, suppose that happened to be true. Well, if so, then it sucks to be humans. But that wouldn't be a plausible metaphysical constraint on the nature of the world itself, unless your metaphysics itself is some kind of humanocentric structure. Which, you know, there are coherent metaphysics where that's true, but it's not normally the. Here's a third possible argument, and this I often hear in conversations with people. Maybe the point is that our pre-theoretic understanding of the world is language first, and mathematical representation is this new and alien concept. So in that sense, the reason we have a language first take is something like it recapitulates humans' development. Our pre-Galileo, if you like, conception of the world is in language, and then mathematics is this new thing we have to learn. Okay, well, it's not clear why, even if that were true, we'd have to meet that demand. I mean, supposing something like a mathematics first account is correct, well, one could perfectly well subsume the particular places where we represent in language into that. I mean, the mathematics first way of talking about representation in language would be something like set theoretic representation. It would be about the correspondence maps between the set theoretic models of one's language or some richer linguistic concept and the antecedent mathematical description system in whatever same or other structure. So I'm not at all clear, even if it was true, that humans just start off doing all their representation in language. That should somehow be a permanent bar to say we require qualitatively different accounts of representation. But in any case, I think that claim about our pre-theoretic understanding isn't true. So here's a bunch of examples where we use mathematics to represent in everyday life, not in the context of high theory. Geometry is the obvious example. And if you think back to, to Socrates in the Meno, Socrates is trying to, teach the slave mathematics. But the form of Socrates' method of teaching the slave is to get the slave to recall or realize themselves that various mathematical assumptions about geometry are true. Plato has in mind that this is evidence that we remember mathematics from previous lives, but the sort of non-Mysterian take-home from it is that we're not blank slates as regards geometry. We have substantial innate knowledge of geometry, which we're able to bring forth. Kant's use of geometry and his notion of the synthetic a priori draws on exactly the same ideas, and there's abundant cognitive psychology, neuroscience evidence in support of modern science. Representation of process and time has similar character. Again, Kant's synthetic a priori appeals to my intuition of time, i.e. my innate grasp of the notions of time. Quantitative comparisons are a nice example. If you think about the way in which I can say, this is longer than that, that's twice as long as that, this plus that's just the same length as that, a whole bunch of notions there, which lead to various constraints on relations that we learn in a first-year logic course, like this relation must be transitive, and even more sophisticated imperatives like he's twice as high as he is. One can find delicate representations of them in the predicate calculus, but they take lots of work to construct, and it's pretty clear that they're built so as to recover an antecedent understanding of how twice as tall as and longer than actually work, rather than constituting our initial understanding. Fluids are continua. We have a pretty good understanding of things like what density is and how fluids can move and how different bits of fluids can move in different routes and how different bits of fluids can have different temperatures. The mathematics to handle that is pretty subtle. So it's clearly we don't have that through having explicitly learned it. But it's also true that we don't have straightforward predicate logic descriptions of that stuff that we're using when we're theorizing. This is the comment I made the first time I gave a version of this talk. She's learned how to do it now, but at the time, my daughter hadn't worked out how to count up to 20. She got stuck at 14 and accidentally went back to 13. Got in the loop. But she had a perfectly good grasp of the fact that the water at one end of the bath is warmer than the water at the other end of the bath. If we were to do radical interpretation of humans, we would have attributed to us a whole bunch of mathematicized representational capacities, which are additional to, albeit overlapping with, various forms of linguistic representation. And again, I'll defer to experts here, but I think neurologically, evolutionarily, it's implausible in the extreme that our various representation capacities are grounded in some shared linguistic representation. I haven't even talked about non-linguistic animals yet. So I want to suggest that it's just wrong that somehow we start with a non-mathematized conception of the world and then learn this new trick. Our understanding of the world has always been mathematized all the way through. Okay, let me wrap up. So, first conclusion, it's impossible to state how a mathematical system represents a physical system without already being able to represent that same system. That's not a vicious circularity. It doesn't prevent us giving a substantive account of what mathematical representation is and saying substantive things about that account. It also recurs in extant accounts of linguistic representation and looks at it. And there's no good case that mathematical representation is fundamentally derivative on representation in natural language. So I could stop there, but I just want to finish with a sort of lesson for philosophy of physics I think we can get from this. There's a nice engagement with these ideas from a different perspective of mine by Caspar Jacobs, who some of you might remember from being a postdoc here 2 years ago. Caspar says, on any, and this is sort of in response to my Stating Structural Realism paper a couple of years ago, for those of you who looked at that. Caspar says, on any account of interpretation compatible with math first realism, it's in square brackets because he's British and refers to maths first realism. Any account of interpretation compatible with math first realism, however, philosophy of physics becomes a radically different enterprise. If roughly the position I've just given is true, mathematical models acquire content by the way in which they're used in practice. The aspirant interpreter should therefore engage in a project of radical translation by studying the way in which physicists use their theories, or go native and join the ranks of physicists, of scientists themselves. And Caspar presents this, I think, as it's like a sort of Armageddon for philosophy of physics. And I think he's very active. I mean, I think if go native and join the ranks of scientists themselves means take a couple of grad classes, then I think it's a more innocuous piece of advice than it might seem. But I do think there's a lesson there, and I do think there's a genuine issue about how one conceptualizes the task of the philosophy of physics. Because very often, what one does as a philosopher of physics is open the physics textbook, read the chapter that describes the formalism, start reading the second chapter that begins applying the formalism, start getting annoyed about the philosophical complexities, and go to the philosophy literature. And if the kind of account I'm giving is right, then one will never get a full understanding in the literal sense of what a physical theory is by that way of trying to learn a theory. If one actually wants to learn a theory, one needs to understand it as it's interpreted, which means if you want to understand a physical theory, you don't just need to learn the formalism, you need to learn how to represent. Thank you.
Break, 2 minute break, get some coffee, if there's some left, because there's no bagel left. And then let's reconvene in case of curiosity.